very accurate over pressure or temperature. And sometimes that is adequate for certain customers. And that is a customer where the pressure level doesn't change much and the temperature doesn't change very much. That often occurs in groundwater installations where you may not have much groundwater variation and the groundwater temperature remains fairly constant. However, if you have any application where the groundwater might change, such as a pump down test, or if you're located near a production water well where a cone of depression is changing rapidly with time, you will need the full pressure range of accuracy. Also, if you're working in streams, lakes, wetlands, where it sees the ambient temperature, and there's quite a range in ambient temperature, it needs the good temperature compensation that we recommended. A very critical area in your purchasing of the logger is a decision whether you want to go vented or non-vented. Let's just talk about what that means first of all. All pressure sensors measure the pressure or strain across a pressure diaphragm. In the vented logger, barometric pressure is brought to the backside of the pressure sensor diaphragm by way of a vent tube in a cable that needs to be extended above the water surface. The front side of the diaphragm sees the water pressure. The pressure measured by the sensor is entirely due to its depth in water. In the non-vented logger, the back side of the diaphragm sees a vacuum, and the front side sees the sum of barometric pressure plus the water pressure. To accurately measure water level, barometric pressure must be logged and subtracted from the non-vented logger pressure data. There are pros and cons for each approach. The vented logger has the highest accuracy. It requires the smallest range transducer. If you're in 5 psi of water depth, you simply need a 5 psi sensor. For the non-vented logger, in 5 psi of water depth, you need 15 psi of barometric pressure plus 5 psi of water pressure, or you need a 20 psi sensor. So you need a larger range sensor, which inherently is less accurate than the smaller range sensor. Secondly, the inaccuracy of measuring the barometric pressure data also makes the non-vented logger less accurate. However, the vented logger has significant reliability and maintenance issues. Keeping that vent tube clear from water, from condensation, is quite difficult and needs significant maintenance. Regular maintenance may not be difficult in your application, and if that's the case, then the vented logger might be the approach. But extra maintenance trips can be expensive depending on the distance you need to travel, and it requires changing of the desiccant to keep it clean. The non-vented logger gives you an accurate measurement, not quite as good as the vented logger, but nevertheless it's easy to deploy, easy to maintain, and usually gives you very good data. As far as the barometric pressure reading goes, it does help to have a second pressure logger in the area, although one can use hourly local weather station data if required, and if the software that comes with the system accepts external barometric data and has the ability to interpolate the data so that sample rates and start times do not need to be controlled. Next, we'll consider logger materials. And it's important that you look at what the material construction is of the logger. The questions you need to ask are, will the environment corrode the logger in installing it? In the opposite way, will the logger itself contaminate the well water you're placing it in? If you're doing sampling of that water and doing chemical tests on the water, you may need to know what kind of chemicals are emitted by the logger. Thirdly, could the logger be frozen in ice? Can the logger withstand ice, or do precautions need to be taken? Or is there a temperature extreme you're thinking of installing this device in? In the case of the corrosion aspect, that is, how does the environment affect the logger? Most loggers are made out of 316 stainless steel, which is pretty suitable for most applications, and they usually have pressure transducers made of stainless steel or ceramic. Either is quite able to withstand most freshwater applications. But as the corrosion potential increases, such as a long-term seawater deployment, where crevice corrosion might occur in stainless steel housings, the stainless steel can be replaced with titanium. Or alternatively, if you have enough room, one could put the stainless steel unit in a sealed bladder sealed in with fresh water that allows the pressure to be transferred, but not the salt water. This approach, however, is only useful for non-vented lagers. You can't extract the vent tube from that. In the reverse form, chemical interference, 316 stainless steel and ceramic usually does not release any chemicals that would affect you. Oftentimes there's plastic caps involved. The only way to know for sure is to take a lager and place it in water and do a chemical analysis in fresh ionic water to see what kinds of chemicals are emitted from the lager. One can have contamination from potentially O-ring lubrication that might be used in the lager, so actually testing is probably required. The frozen lager, the sensor mounting should preclude excessive expansion of ice pushing on the diaphragm. That's really a design issue. The stainless steel pressure transducer is a little more susceptible in that its diaphragm is a thin foil of stainless steel that's easily permanently deformed, whereas the ceramic is more of a hard plate, although it can also be cracked. As far as temperature extremes go, typically the lagers can't withstand very high temperatures because they're limited by their battery performance, and batteries can't deal with too much temperature. And most of the lagers are temperature calibrated. As I discussed, in our case, we pressure cycle and temperature cycle them and calibrate them over a range of 0 to 40 C. So that's pretty much the temperature range it's expecting to see in standard water applications. Up through lager material. At this point, I'm going to hand it over back to Nick.
Okay, thank you, Richard. One of the things that I think a lot of people sort of forget about until the end, so they're actually trying to use their new lager, is how do you communicate with the lager? And one of the first communications-related questions that you probably want to ask before you select a lager is how do I actually communicate with the lager? In this day and age, virtually all water level lagers communicate with a host computer either using USB or a serial interface. This day and age, USB is generally a lot easier to use. It's generally significantly faster. And today, a lot of PCs don't ship with serial ports anymore, so you end up needing to use a USB to serial adapter, which is a little bit clunky. But there are some pros and cons to both. If you're already set up on serial, it's not that bad. But the USB is just nice to know, plug and play, and you're ready to go. Another question you got to ask is how do I actually make that connection with the lager to communicate? Number of lagers out there are made with a optical interface. Nice thing about the optical interface is that you don't need to actually open up the lager to make the connection. Generally, they communicate through some sort of window. That's nice when you're out in the field because it seems like it's always raining on the days you need to download, and you don't have to open that logger up and expose the electronics to any moisture. Then you also should consider what are my offload options? On a standard data logger, the two obvious options are always that you can either bring the logger back to your office or you can bring a laptop. But there are a couple other options, such as data shuttles. Data shuttles can be real handy. They're generally fairly inexpensive, generally able to take a fair amount of abuse. Many of them will